example of the linear wave equation has shown us that straightforward application of finite difference approximations to a given differential equation does not necessarily give us proper results. We have seen in fact 3 different ways of discretizing the equation, and we have seen that in all cases the solution has been not so exemplary. Okay, the solution that we got from the by applying the finite difference approximations and then doing the corresponding computation has not given us the correct solution or anything resembling the correct solution, except for one particular combination of the parameters where the Courant number was equal to 1. So this should give us, this should tell us that there is something more that we need to do in terms of what kind of approximations that we make before we can start solving them. So what it amounts to saying is that although we can write down approximations, finite difference approximations of a given accuracy for a given derivative, not all approximations will give us a proper solutions. There are some which are better than some others. How can we say which is better and which is not good? Because in the general case, when we try to solve Navier-Stokes equations using this particular way, then we do not know the solution, and if we knew the solution we would not be doing the CFD solution at all. Okay, so if you do not know the solution and if your numerical method is likely to give rise to errors, then how can we accept such a solution method? Because how can we distinguish the errors from the real solution when we apply to a practical case where we do not know the solution and where we depend on the accuracy of the method to provide the correct solution. So we need to have some method, some way of saying, a formal way of saying that if we do this kind of approximations and if we follow this kind of procedure, then we will get a satisfactory solution. Okay, so that kind of assurance is necessary, and that kind of assurance is what we are going to discuss in this class. So we are looking at the general case of the scalar transport equation with a time dependent term, an advection term, diffusion term and a source term, and we are looking at a specific idealization of that in the form of the wave equation. And when you look at that, there seems to be no reason why our approximation should give a wrong answer, except for the fact that we have a truncation error, okay, except for the fact that we are approximating the derivatives with finite difference approximations of first order or second order, and in the process of doing this approximation we are neglecting certain terms, and it is it because of the combination of this approximation that is actually causing this? So this is one question, and the other question that we have to ask is that is there a combination which will give us a proper solution? Okay, so we have to look at what kind of combination, and is it all a question of accuracy or is there something more to this, and is there any guarantee, for example, that we are solving the right equation? Is our solution, the computed solution, not good because we are not solving the right equation, or is it not good because we are solving it only approximately? Because any numerical computation, any computer based solution with finite precision of accuracy is always going to be approximate. So is it because of those kind of considerations? What is the guarantee that the computed solution will approach or will be equal to the exact solution of the governing equation? Okay, so these are the questions that we have in mind, and these are the questions that we will try to address through a formal procedure of the analysis of the discretized equation. Okay, so now we can begin to understand, begin to see some points that we have to consider. Firstly, we are solving the partial differential equation in an approximate way, okay, in the approximate way by writing an approximate form of the derivative, and we are solving it in a discrete way. We are not looking at a solution which is continuous, we are looking at only discrete points, okay, and we are doing a method of solution which has finite precision. So we can see that the computed solution is different from the exact solution in 3 different ways. One is that instead of looking at phi of x t, we are looking at phi of xi t n. So it is at a discrete points only. And second thing is, instead of getting an exact solution at xi t n, we are only getting an approximate solution which satisfies only the discretized form or the approximate form of the governing equation. On top of that, we are getting a solution which is not even an exact solution of the approximate form of the equation, because we are not doing exact arithmetic, we have only finite precision arithmetic. So there are this kind of errors, okay, this kind of discrepancies may be playing havoc with our solution, because of which we are getting a wrong answer. Okay. So let us therefore try to answer questions related to this. Okay. So this kind of analysis, these analysis of the condition of a computed solution approaching the exact solution of the partial differential equation is put up in 3 different stages using 3 conditions known as the consistency condition and the stability condition and the convergence condition. Okay. So when we say consistency condition, we are talking about is the discretized equation a very good replica of the actual partial differential equation. So that is, can we claim that the discretized equation would approach the exact equation if we make our discretization very small. See, we are saying that we are not looking at phi of xy, we are looking at phi of xi t n. So that is at discrete points. So if we had the capacity to make delta x very small and delta t very small, so that we are approaching almost a continuous variation of xi and tn. So in that case, can we claim that our discretized equation, the approximate form of the equation that we are solving, can we say that this approximate form will approach the partial differential equation? So this is known as the consistency condition, the consistency between the partial differential equation or the governing equation and the discretized equation. Okay, so we will put this as consistency, where we are looking at the assurance that the discretized equation is the same as the partial differential equation in the limit as delta x and delta t tending to 0. The next question is about the solution method. Okay, so if provided we have this consistency condition satisfied, provided we can show that we are solving the correct equation which has the property of going to very small delta t and approaching the exact solution for very small delta t and delta x. Now this point is important, because we saw in the examples, especially with the FTFS method and the FTCS method, which is central in space methods, no matter how small the delta t was, we are still getting a wrong answer. So even if those methods are such that even if you made the delta t and delta x very small in the computed solution, even then the computed solution will not give us a proper solution which compares favorably with the exact solution. So it is not that if in all conditions, if we can make delta t and delta x and other discretizations very small, we cannot guarantee that the solution would automatically approach this. So that is why this query about whether or not the discretized equation would approach the exact equation for very small delta x and delta t is a justified query. Okay, so we have to consider that, and that is where this consistency condition is. Now once we have satisfied ourselves that we are solving an equation which is consistent, then the second question comes, are we solving it properly? Okay, are we solving it properly in the sense that does the discretization does the discretized equation have a property of amplifying errors? Again, when we go back to the example of FTFS and CT, FTCS and even FTBS, we saw that there are the solutions seem to be getting out of control, out of bounds. The expected variation of phi was between 0 and 1, and the computed variation of phi was something like plus or minus 400 within a few time steps, within 5 time steps in the case of FTFS method for certain conditions. So it seems to be amplifying errors, whereas the true solution we know is just something which is nicely being uniformly being carried forward in the x direction. So the true solution of the governing equation is not going to does not have this feature of amplifying errors, but the discretized form, at least in some discretizations, seems to be having this nature of amplifying errors. So this brings us to the second condition of stability. Okay, so does the discretized equation have the property of stability, whereby errors that are introduced from whatever reason, from finite precision arithmetic or from rounding off errors, okay, or from boundary conditions or from truncation errors, errors related to discretization, all these kind of errors, or even simple typographical mistakes, okay, those kind of things. Such errors, do they have the property of getting amplified, or is the scheme stable in such a way that those errors will be suppressed and attenuated, and finally as time progresses we get to a stable solution. So the second question then therefore is stability. So far what we have been looking at is whether the discretized equation is very good approximation of the partial differential equation, and we are looking at whether the discretized equation, the computed solution of the discretized equation has a property of amplifying or attenuating the errors. We have not said about the comparison between the computed solution and the exact solution. Okay, so we are talking only about the method of solutions so far in the consistency and stability conditions, but now is the time for us to look at the equivalence between the computed solution and the exact solution of the governing equation at those discrete points at which we are looking at. This condition where we are saying that the computed solution at those discrete points would match with the exact solution at the same discrete points is known as the convergence condition. Okay, convergence. Okay, so if you have a scheme which is convergent, then we can say that the computed solution would approach the exact solution at xi tn. Okay, so the convergence criterion is about the computed solution and exact solution. Now how is it different from stability? Stability is only about the discretized equation. Okay, so the computed solution of the discretized equation, okay, dE, discretized equation, approaches the exact solution of the discretized solution. Okay. So, this stability condition refers to, it poses the query on whether or not the computed solution with all those errors and the amplification features, whether or not it would be an exact solution of this. And convergence is talking only about the computed solution and the exact solution of the partial differential equation. Okay. Consistency is not about solution, it is only about whether the discretized equation approaches the partial differential equation, okay, the governing equation. So, there are three different conditions. We are addressing three different issues. Ultimately, we want convergence. Ultimately, we want the computed solution to match with the exact solution of the partial differential equation at the points xi and tn. But in order to get here, we have to pass these two hurdles. We have to make sure that we are getting this computed solution in the right way by ensuring that we are solving the right kind of equation, and the equation that we are solving has the right kind of stabilization or attenuating properties, so that errors do not get amplified and spoil the solution. Okay. So, this condition, this triple criterion here will, if we can satisfy these conditions, the consistency condition and stability condition and convergence condition, then in such a case we can say we can have confidence in our computed solution. We can have confidence that the computed solution will approach the exact solution of the partial differential equation at those grid points at which we are computing. Okay. It does not mean that the computed solution is error free, because for any computation we must have some delta x and some delta t. Okay. So, that means that there is some discretization error, there is an error of approximation that is there, but with this, if we satisfy the consistency condition and stability conditions, then we know that this error is contained, is bounded, it does not get amplified and that it does not give us any problems. Okay. So, in that sense, if we are able to satisfy the convergence condition while simultaneously satisfying this, then we can say that the computed solution at space point I and time point n will approach the exact solution, okay, which I am denoting by this, at that particular point, subject to plus discretization error, or we can call this as truncation error, which depends only on delta t and delta x, and these are in our control. Once we have a computed solution which is not very sensitive to delta t and delta x in terms of delivering a proper solution through the stability, okay, then this is in our control and we can reduce delta t and delta x to as low as possible as we want, and then we can make our computed solution approach the exact solution. Okay. So, and we can minimize the error as to as low as what we desire as is required for the solution. Okay. So, in this, under this condition, we can say that a grid independent solution now, what do we mean by grid independent solution? A solution which does not depend on either delta x or delta t. Okay. So, it is which does not vary with successive reduction of delta x and delta t. Okay. So, let us say that you have a square duct and you have a 20 by 20 grid. So that means that for the same length you have 20 intervals in that. So that gives you a certain delta x. You make it 40 by 40, you are reducing delta x by half. You make it 80 by 80, 160 by 160, 1000 by 1000. And what you will see is that as you make the grid finer and finer, obviously the computation cost increases because the matrix A that leads to the differential algebraic equations, that becomes bigger and bigger. But if you did not have any constraints on the computing resources, then you could make it as high as possible, and as you keep on increasing the grid size or the number of grid points, and as you keep on decreasing the delta x and delta t, then the parameter that is of interest to you, for example if you are looking at the pressure gradient, pressure drop in that particular duct for a given flow rate. Okay. So in such a case you will find that after some number of grid points, the computed pressure gradient does not really change much. If you reduce the spacing by another half, it does not give you any significant variation in the parameter of interest. So at that point you can say that my computed solution, which is of interest to me, okay, which I want to get from my CFD calculation, is no longer sensitive to the delta x and delta t. So that is what I call as a grid independent solution. So, and grid independent obviously means not only delta x but also the delta t if you are looking at a time dependent problem, and we can say that the grid independent solution is almost equal to the exact solution of the governing equation. Okay. So the satisfaction of these things is as powerful as this, that if we are able to generate a grid independent solution, then we can rest assured that it is almost as good as the exact solution of the governing equation. Okay. So this is the kind of power that is there in these three conditions, that if we are able to demonstrate the consistency, stability and convergence of our numerical solution procedure, then we can claim that the grid independent solution which we obtained from the computer from the procedure is the exact solution of the governing equation. But the caveat is that if we want to have this is the desired condition, okay, this is the desired guarantee that we would like to have. In order to do this, we need to prove these three. Okay. These three are not, they are related in a way, okay, and these three, for the case of a linear problem, for a linear partial differential equation, then there is a theorem called the equivalence theorem of Lax. Lax is obviously a mathematician, and it is not the laxity on the part of Lax, is actually made a very nice theorem which is for a linear well posed mathematical problem of in the form of a partial differential equation. The equivalence theorem says that consistency and stability are sufficient to guarantee convergence. Okay. This is in a way a bit of layman speak, but the point is that if we are able to show the consistency of our discretization and the stability of the computational form computed solution of this, then we can rest assured that we will have convergence condition is satisfied and convergence is guaranteed, and under those conditions we can say that the difference between the computed solution and the exact solution has a discretization error which goes to 0 in the limiting case as this thing go to 0, and in the limiting case as the n tending to infinity. Okay, so in that sense the two will approach. So this is a very useful thing, but like all mathematical theorems it is also not of a great practical value from the fact that this is limited only to a linear equation. Okay, so when you have a linear partial differential equation, then this theorem works. For a nonlinear problem, which is what we normally have in our CFD, then this theorem does not work. Obviously it is only for linear thing, but in such a case we have to do local linearization. We can convert the nonlinear problem into a linear problem, and then for that linearized problem we can check for consistency using this. So in that sense it is not something we can brush aside as being useless, but at the same time it tells us that for a under linearized condition, if we are able to check for consistency and stability, then we can get the guarantee of convergence. And while this theorem has those kind of limitations, experience has shown that if you apply standard methods for the analysis of consistency and stability, and if you follow these as practical guidelines for determining the parameters that you are going to employ like delta t and delta x, then in most of the cases we do get a good solution. Okay, but it is not guaranteed, and we also have to worry about other reasons for getting a non-converged solution and so on. But in general this is a good pointer, and it's an indication of why and how problems may arise. Okay, so let's take it for granted that this is a useful thing for us, useful pointer in terms of what kind of approximations that we have to that we are allowed to make for derivatives so as to get a proper solution. And let us investigate this further, and let us investigate how we can prove the consistency and stability of our discretization scheme, because now the problem reduces to how we can demonstrate consistency. If there is a method by which we can demonstrate the consistency of our method, and if there is a procedure by which we can demonstrate the stability, then we can apply these methods to each discretization that we propose and see whether the discretization satisfies these conditions. If it does, then we can proceed with the solution procedure. Otherwise, if it does not satisfy, in such a case we have to look for alternate ways of discretization. So now let us consider how we can do consistency. We have said consistency is a condition which tries to look at whether or not the discretized equation will approach the partial differential equation under the condition of delta x and delta t tending to 0 and any other. If you have a 3-dimensional equation, then delta y tending to 0 and delta z tending to 0 and so on. And so we are looking at, we have to see under what conditions the discretized equation tends to the partial differential equation. So when you pose a question like this, then we can see we can start by examining what is the difference between the discretized equation and the partial differential equation. Okay. We know that the two differ only by the fact that the discretized equation is an approximation of the partial derivatives of the derivatives appearing in the equation, and each derivative has an approximation which is given by the Taylor series approximation. Okay. So, if you go back to the Taylor series expansion and then look at the error that has arisen in making a particular approximation, then we can say that the difference between the discretized equation and the partial differential equation is the truncation error that is resulting from the approximation of each derivative that appears in the partial differential equation. Okay. So, if you have 5 derivatives, then each derivative is approximated in a particular way using a finite difference approximation, and that part each derivative will have its own truncation error, and the combination of all these truncation errors is the difference between the discretized equation and the partial differential equation. So, if we can show that the truncation error goes to 0 as delta t, delta x, delta y, delta z tend to 0, then we can claim that the discretized equation will approach the partial differential equation. Okay. So, we can say that the truncation error, we are saying that truncation error, we are calling it truncation error because in writing a finite difference approximation, we are truncating the Taylor series which has infinite number of terms to first 3 terms or first 4 terms and so on. Okay. So, the rest of the terms are neglected. So, the neglected part is the truncation error. So, the truncation error of the discretized equation between the discretized equation and the partial differential equation, which we are calling as say dE minus PDE, this should tend to 0 as delta x tends to 0 and delta t tends to 0 in the case. Okay. So, the consistency condition does not say that the two must be equal, it only says that it has the property that the difference will tend to 0 in the limit as delta x tends to 0 and delta t tends to 0. We are not claiming that there is there will not be any difference, we are only saying that the solution method has the capability of reducing the error to as low as is required as is possible. Okay. So, it only that the difference will tend to 0 as delta x is made to go to 0 and delta t is made to go to 0. Okay. So, then in order to verify the consistency, we have to look at the truncation error. So, let us do that. For the simple case, the method is very general. We have considered dou phi by dou t plus u dou phi by dou x equal to 0, and in the let us consider the case of ft fs, that is forward in time and forward in space. And why would we want to consider this? Because this has given us an immediately nonsensical answer for whatever values of delta t and whatever values of Courant number that we have taken, and not only that, it has really blown up very fast compared to FTBS or other schemes. So, we can take this as an example and see whether the FTFS approximation for this particular equation has the will satisfy the condition of consistency. So, when we write the FTFS approximation, we are writing this as phi I n plus 1 minus phi I n by delta t plus u is being taken as a constant. In the example, we have taken it as 1 meter per second, phi I plus 1 n minus phi I n by delta x equal to 0. Okay. Now, this is an approximation, first order approximation, and that results from the expansion of phi I n plus 1 as phi I n plus delta t phi t at I and n, where phi subscript t is actually dou phi by dou t. Okay, so delta t square by factorial 2 phi tt indicating the second derivative, delta t cubed by factorial 3 phi t t t I n and so on. So when we make use of the first 3 terms, okay, first 2 terms in this, then we get an approximation for phi t, which is dou phi by dou t as this particular thing. So we can say that the truncation error resulting from this approximation is this whole thing, and similarly the truncation error resulting from this approximation is the same, very similar to this, except that instead of delta x we have delta t, we have delta x, and instead of derivative with respect to time we have derivative with respect to space. So we can say that the truncation error from the FTFS scheme for this will be given by delta t square by factorial 2 dou square phi by dou t square at I n plus delta t cubed by factorial 3 coming from if we take the first 2 terms in the time derivative plus u delta x square by factorial 2 plus u delta x cubed by factorial 3 dou x cubed I n plus so on. Okay. So this is the difference between the discretized equation and the partial differential equation, with either plus or minus depending on whether we do dE minus PD or PD minus dE, okay, but it varies like this, and in this u is a constant, and we are looking at what happens to the truncation error as in the limit as delta x tending to 0 and delta y tending to 0. Okay. So we can see that we can look at each term here, delta t goes to 0 as this goes to 0, this thing goes to 0, this thing goes to 0, and this also goes to 0, go to 0, so that in the limiting case of delta x tending to 0 and delta t tending to 0, the truncation error goes to 0. Okay. And we can see that if you make delta t very small, then this term, which is constant, see for a given functional variation of phi with respect to t and x, then the derivative, the second derivative at a particular point with respect to time, and the third derivative, and okay, and the spatial derivatives, these have fixed values for a given phi of xt. Okay. So these will not change with in the exact case with changes in delta x and delta t. So once these are fixed, then this thing can be made as small as possible as delta t and delta x tend to 0, and they can be made to go to 0 for very, very small values within machine error and so on. Okay. So we can say that limit of the truncation error in these cases is equal to 0. So that means that the FTFS scheme satisfies the consistency condition. So we can see that FTFS scheme has a truncation error which reduces to 0, which goes to 0 in the limiting case of delta x and delta t tends to 0, and we can also show similarly that FTCS scheme and FTBS scheme, all the three schemes that we have employed for this equation, they go to they satisfy the consistency condition. So at least from these examples we can confidently say that the approximations that we have put here are consistent, and we can also confidently say that consistency condition alone does not guarantee us a proper solution, because with even though these satisfy the consistency condition, we saw that the computed solution seemed to be not so good. Okay, so we have to look at the second aspect of stability to see whether they satisfy the stability condition. But when you look at this consistency condition like this, and we see that it almost looks like every scheme that we consider must obviously satisfy the consistency condition. So is it that consistency condition is superfluous by the very fact that we are using Taylor series expansion for writing the approximations, and we are using the same analysis for looking at consistency? Is it superfluous, or are there cases where the equations are not consistent? The most famous of this those inconsistent cases is probably the Dufour-Frankel scheme, discretization, for a different problem, for a problem which can be written as dou u by dt dou t equal to nu dou square u by dou x square. Okay, so this is written for different cases, but in this case u here represents a velocity and t is obviously time and nu is the kinematic viscosity. One can see this as a fluid mechanics problem, and this is also known as the Stokes first problem, which arises, for example, when we consider the case of an infinite expanse of fluid, let us say liquid, and you have an infinitely long plate, thin plate, which is submerged in this fluid and it is horizontal at a particular depth, and at time equal to 0 you suddenly set this infinitely long wide thin plate into motion in the horizontal direction, that is in its length direction, at a uniform velocity of a capital U. Okay, so because the fluid that we are considering is a real fluid with real viscosity, and because of the no slip condition, the fluid which is adjacent to the plate will start moving. So we will find that because of the plate movement in this direction, the fluid which is above it also starts moving, above it also starts moving, and above it also starts moving. So the variation of the development of the velocity profile with respect to time is encapsulated in this equation, is given by this equation, and this is known as Stokes first problem. So this is not any artificial problem, this is a problem which is quite a fluid mechanics problem. And not only that, we can see that this is also in a way a subset of the generic scalar equation. If you were to substitute u for phi here like this, then it becomes like the accumulation diffusion problem. Okay, so the transient diffusion problem, and it is also a transient heat conduction problem is given by the same equation. There are a number of cases which are also given by this, and it is also a simple equation. Now we can write many kinds of finite difference approximations for this, and we can, for example, write ui n plus 1 minus ui n by delta t equal to nu times u I plus 1 n minus 2 u I n plus u I minus 1 n by delta x square. Okay, so this is forward in time and central in space. We know that this is and this is explicit. So our first intuitive way of writing a finite difference approximation is like this, because this is a self-starting method. As part of the initial condition we know uin, so we can compute the uin plus 1, and this is first order accurate, but we are okay with that first order accurate given that this is a self-starting problem and we can start implementing it straight away. And it is quite easy to have a second order approximation for this without too much of complexity. So this is first order in time and second order in space, and it gives us a nice and easy expression in terms of an explicit method for the calculation of ui n plus 1. So the solution seems to be nice and smooth, okay, in terms of implementation. But when you actually try it, and having seen the difficulty with another simple linear wave equation that we have considered, that we should be suspicious as to whether or not we get a proper solution. And in fact one will show later on that the solution that we get from this FTCS explicit equation for this is only conditionally stable, in the sense that only for certain range of values of delta t and delta x can we hope to get a good solution, and in other cases we will not get a good solution. Okay, so in that sense this is only it's only conditionally stable. And the stability condition will be that mu delta t by delta x square must be less than or equal to half. So for a given nu, which is the kinematic viscosity, and delta x for a given grid, delta t must be less than the value given by this. If it is more than that, then we will not get a proper solution. So that means that we are limited in how fast we can go forward in time, because our time step is limited by this. So it would be nice to have something which is unconditionally stable, okay, something which will allow us to choose any values of delta t and delta x. And it would also be nice to have not a first order accurate but a second order accurate approximation for this. Okay, so with that, if you were to say that let me not take a first order accurate thing and I will make it second order accurate, then I can, for example, I can write this as ui n plus 1 minus ui n minus 1 by 2 delta t. Will make this as central in time and central in space, explicit, still explicit. So this is second order accurate in time and second order accurate in space. So that is much better than the FTCS scheme, because that is only first order accurate in time. But if you do this, if you try this, then you will find that it is no longer conditionally stable. In fact, it is unconditionally unstable. That means that no matter how small delta t and delta x that you choose, you will always get an unstable solution, and we have actually got something like that in the case of FTFS scheme for the linear wave equation. Okay, so we have seen that kind of thing. So a straightforward, a naive approach to improving the accuracy of a scheme, which seems to be mathematically okay, it has actually spoiled the conditional stable condition and has made it into unconditionally unstable condition. Okay, so if you want to have more higher accuracy and so on, if you want to have a second order accurate thing, then this is obviously not correct. So this is where Dufour and Frankel have stepped in, and they have said that let us not go for a fully, if you look at the Stokes first problem, FTFS scheme which is only first order accurate is conditionally stable, central in time and central in space is second order accurate, but it has become unconditionally unstable. Therefore, if you want to increase the accuracy of time, then we are having to compromise on the overall solution itself. This is where Dufour and Frankel have stepped in 1953 and proposed a small modification to the way the CTC scheme is implemented. We have a central in time, central in space as given by ui of n plus 1, ui of n minus 1 by 2 delta t, which makes it central in time, and central in space, which is given like this, and this is unconditionally unstable. So we cannot hope to get a reasonable solution with this. So what Dufour and Frankel have suggested in 1953 was to replace this uin as ui n plus 1 plus ui n minus 1 by 2. So it is taken as the average of the previous time step and the coming time step, and then if you now substitute this into this, then this 2 and this 2 will cancel out, and we will have ui n plus 1 minus ui n minus 1 by 2 delta t equal to alpha nu by delta x square times u I plus 1 n minus ui n plus 1 minus ui n minus 1 plus ui minus 1 n. So this is another way of calculating this ui n plus 1, and this is a second order approximation, it being a central approximation. So the overall scheme has not compromised on the second order accuracy of either delta t or delta x. So the overall scheme is delta t square and delta x square. Okay, so we have retained the second order accurate nature of this particular discretization, and not only that, if you look at the terms here, ui n plus 1 is appearing here, otherwise it is n minus 1 which is known, ui plus 1 n which is known, ui n plus 1 is the value that we are actually seeking. So in a way this is nothing new, and you have n minus 1 here and n here. So in that sense this can be evaluated explicitly. So not only has this retained the character of second order approximation here, this is also an explicit method, which is therefore easy to solve, which is easy to compute. And the difference that this makes as compared to the standard CTS scheme is, whereas this is unconditionally unstable, this is unconditionally stable. That means that you are free to choose whatever value of delta t and delta x that you want to get, and it will not amplify errors, okay, which is very rare for an explicit method. So in that sense this is unconditionally stable, and we have gotten rid of the conditionally stable restriction with the FTFS scheme, and we have completely overturned this unconditionally unstable thing while retaining the same ease of computation in the form of explicitness and the same accuracy of computation in this. So in that sense this simple modification that is made here is a brilliant modification, and it has given us a lot of advantage in this. Okay, therefore it is always nice to explore what approximations we can make in order to improve the solution, but it does not stop there, the story does not stop there. If we were to look at the truncation error of the Dufour-Frankel method, we will see that it has it is of this particular form. Okay, the third derivative times delta t square plus nu delta x square by 12 u x x x x, that is the fourth derivative, minus nu delta t square by delta x square times u t t. All derivatives are evaluated at x, plus nu delta x 4 by 360 times u x x x x x x, that is the sixth derivative, plus nu delta t square t 4 by delta x square by 12 delta x square, fourth derivative of time, and so on, okay, like this. Now the leading terms in the truncation error are second order thing here and delta x square here, and this is delta t by delta x square. Okay, so we can say that the order of accuracy of the Dufour-Frankel scheme is delta x square, delta t square, and delta x by delta t by delta x whole square. Okay, will this go to 0 as delta t and delta x go to 0? It is not necessary that as delta x and delta t tend to 0, then these two terms will go to 0, but this term need not go to 0. For example, there can be a fixed ratio in which these two are varying, and while both of them are going to 0, this need not go to 0, and therefore this thing will not go to 0. Okay, so whereas this goes to 0, and this also written as delta t square by delta t square by delta x square. Okay, like this will also go to 0. So for example, if you say that delta t by delta x is a constant b, then we can write the truncation error of Dufour-Frankel scheme as minus delta t square by 6 third derivative plus nu delta x square by 12 fourth derivative minus nu b square second derivative of time plus nu delta x 4 sixth derivative with respect to x plus nu delta t square b square times the fourth derivative with respect to time. Okay, so in this, as delta t tends to 0 and delta x tends to 0, this will be 0, this will be 0, even this will be 0, because even though b is constant, this is 0 and this is 0, and so on. Okay, so the rest of the terms will also go to 0, but what we are left with is this particular term. Okay, so from that point of view, the Dufour-Frankel scheme does not have a truncation error which goes to 0, but which goes to nu times b square times u delta t, u second derivative of u, so that the Dufour-Frankel scheme is an approximation not of this, but this equation dou u by dou t plus nu b square dou square u by dou t square equal to nu dou square u by dou x square. Okay, so the Dufour-Frankel scheme is a proper approximation of this particular equation rather than this equation, and therefore it approaches this partial differential equation and not this partial differential equation. So in that sense it is inconsistent. Okay. So the Juffo-Frankel approximation with all the desirable features in terms of getting us a second order accurate solution in an easy way and without any restrictions on the delta t and delta x is actually inconsistent. Okay, but what we can see also is that it is consistent when you are looking at time independent solution. If you are looking for a steady state solution, this term will go to 0 anyway. So the steady state solution obtained by this method will be a consistent solution. Okay, so in that sense if you are looking at a steady state solution from this transient solution, which is very commonly done in CFD solutions, because that is probably one of the ways of overcoming the inherent nonlinearity contained in the Navier-Stokes equations. So in such a case the final solution is not arising from an inconsistent discretization, but the way to that steady state solution is definitely going through an inconsistent approximation of the governing equation. So whatever error that arises from this term, which depends on what the value of b is with respect to and what the value of the second derivative is with respect to these other terms. So depending on the magnitude of this as opposed to the magnitude of these two at a particular time and space will actually determine the accuracy of the time dependent solution. Okay, so even though it is it has all desirable features, the solution that is the transient solution that we get from this need not necessarily be converging towards the exact solution of this partial differential equation. So that is what we mean by lack of consistency. So it is not that every scheme that we do is consistent, and it is also that arbitrary approximations that we make, for example saying that UIN is the average of the two things here, okay, can lead to inconsistent solutions, okay, inconsistent formulations, and we have to be aware of that. We have to do a consistency check of our governing discretized equation in order to see that in the limiting case the assurance that we are actually solving an equation which resembles very closely the partial differential equation is very important.